In continuing to look at electrostatics, we're now going to have a look at electric potential energy. To make sense of that, though, we're first of all going to look backwards into some concepts that we've covered previously, and that relates to gravitational fields. So in the same way that we can do work on an object when we lift it through a gravitational field, we can do a similar thing with electric fields. So when we lift an object against a gravitational field, so by against I basically mean that the gravitational field lines would be pointing down towards the ground. So if we do work to lift it, that means we're acting against the gravitational field. What it also means is that we're giving that object gravitational potential energy, where the equation for that is mass times acceleration due to gravity multiplied by the height through which it's been raised. So that's going to give it gravitational potential energy. We can do a similar thing if we deal with a charge. So there's the gravitational potential energy side of things. So in that same way, we can do work on a charge, and in doing that work on a charge, that's going to require that we're going to be moving it against an electric field, and in so doing, we're going to be giving it electric potential energy. Now, you could see in the header at the top of this this video that electric potential energy is something that you do need to be able to define. And so if we refer to the glossary here, this idea of electric potential energy is the capacity of electric charge carriers to do work due to their position in an electric field. Now, in the glossary itself, slightly different wording here, the last two words in particular. So I'm changing it here to in an electric field. The glossary itself actually says in an electric circuit. Now, in an electric circuit, you can imagine that there is an electric field set up sort of directed from positive to negative. We're really specifically looking at electric fields here, so I'm going to go with that explanation rather than the electric potential energy that's stated in the glossary. So to make a little bit more sense of that, let's have a look at a charge, capital Q, and it's going to have field lines directed away from it, given that it's a positive charge. I'm not going to draw all of the field lines in here, we only really need some that are in this particular region. And imagine that we have a charge positioned here, that's going to be charge Q, and this location that it's currently in, we'll call it position A, and we want to move it closer to charge capital Q to this point that I've marked there, and we'll call that point B. So we're going to have to do work on that charge because it's going to be moving against the electric field, and so we can identify then the work done in moving the charge from A to B. And the reason why we're doing work here is that we're applying a force in order to get the charge to move through a distance. And the symbol that we're going to use there is delta U. So U being energy and delta indicating that it's a change in energy. So there was already some electric potential energy at point A, and then we're going to increase that by moving it to point B. So that results in an increase in electric potential energy. So that value delta U, while it's the work that we're doing, it also can be considered to be the electric potential energy that's gained by the charge. Just as a side note here, usually to calculate the amount of work done, we'd multiply the force by the displacement through which the force acts. In this situation, we can't do that because the force actually will increase as we get closer to the charge. And we know that because, as we saw in the previous video, the electric field strength closer to the charge is going to be greater because the field lines are more closely spaced. When we move further out, the force is going to be weaker. So in moving from point A to point B, that force is going to increase, and so we can't just multiply by a force because the force is actually changing as we move the charge closer. And the reason why that force is increasing is basically to overcome those Coulomb repulsion forces between our charge lowercase q and our charge capital Q. I should also mention that the charge lowercase q would have to be positive here. If it was negative, then we're not actually going to be doing any work moving from A to B. The charge itself is going to just be attracted to capital Q, and so the field would be doing the work and we wouldn't actually be doing any work. The charge would lose electric potential energy as it moved closer to capital Q. So if we know that there's a change in electric potential energy, but we can't use force times displacement, there must be another way that we can figure out what's happening with the change in electric potential energy. And in order to make sense of that, we actually need to go back to topic 1.3, which was on electrical circuits. The idea that we're looking at here is electric potential difference. Note here that electric potential difference is not the same as electric potential energy. So electric potential is a different quantity to electric potential energy. And electric potential difference, the symbol that we use for that is V, sometimes referred to as voltage, and that is the change in potential energy. So the definition is that it's the change in electric potential energy. Note that I'm saying electric, but I'm writing electrical. It's just habit that I'm used to calling it electric potential energy, but the syllabus uses electrical. So change in electrical potential energy per unit charge. So basically what that means is that we have a fairly simple, straightforward calculation here, that the electric potential difference, V, is just equal to that change in potential energy, and we've already seen that that's delta U divided by the amount of charge that we've got. So that's the equation that we need to consider when we're looking at charges being moved through electric fields. Note that we can rearrange that, and so we could calculate delta U simply by multiplying the charge by the electric potential difference that the charge has been moved through. But you can see there the highlighted version of the equation on the left is the one that's in the data booklet. And just to notate what all of those quantities are, we've already seen that V is the electric potential difference, and that, as I mentioned earlier, is sometimes referred to as voltage, and the units for that then are volts with a capital V. Delta U is the work done in joules, or the change in electric potential energy. And given that it's work and energy, the units that we'll have for either of those two quantities will be joules. And finally, Q is the charge in coulombs. So they're the three quantities that we can use there. So let's have a look at an example question here that uses this equation. And we're going to start off with a charge is being moved, and it's being moved through a 1.2 volt electric potential difference. And the other piece of information here is that a certain amount of energy is needed, and that's 4.5 microjoules of work are done on it. So hopefully you can see there that the question is going to be to calculate the quantity of charge. So the first thing to do here, as I've suggested a number of times before, is to list out the quantities that you've been given. We know that V here is equal to 1.2 volts, and we know that the amount of work, delta U, is equal to 4.5 microjoules, which we can write as 4.5 by 10 to the negative 6, remembering that micro means a factor of 10 to the negative 6. And so the only thing that we then need to do is to calculate the charge. So if we consider the equation V is equal to delta U on Q, we know then that we have to calculate Q, so that's going to be delta U on V. So that's simply equal to 4.5 by 10 to the negative 6 divided by 1.2. Now that gives us an answer of 3.75 by 10 to the negative 6. And we know that that's going to be in coulombs, given that it's a charge, but rounding that to the correct number of significant figures and using metric prefix, we can say that that's 3.8 microcoulombs. So there's a quick calculation to show you how that equation could be used. Two more points I just want to make here. I'm not going to jot these down as notes, but things to just be aware of. If the charge was actually placed at B and then was released so that it then moved towards A, we wouldn't actually be doing any work on the charge. The electric potential energy stored at B would actually be converted to kinetic energy as the charge moved from B to A. So we're only going to be doing work when we move a charge against the field. Similarly, if we were to move the charge sort of perpendicularly to the field line, so in other words, if instead of moving it to B, if we moved it, say, around a circular path to some location here, let's call it C, we're not actually going to be doing any work on the charge there either. So the reason for that is that we're still the same distance away from charge capital Q. So in moving the charge from A to C, we haven't actually had to apply a force to cause a displacement in the direction of the force, and as a result no work would be done there. It's the same sort of scenario as if you are carrying a box from one side of a room to another. Because you're not actually lifting the box against gravity, you're not actually doing any work against the gravitational field. So a couple of points there just to store in the back of your mind. Not things that you, like I say, that you need to be able to write down and explain and define necessarily, but things to just be aware of when you're dealing with how much work's being done or the conversion of electric potential energy into other forms.